All right. Welcome to the third day of the ISSR&D conference technical sessions. This is our first video conference for uh, this event. It's the 2020 online series. We do encourage you to go to the online ISS conference website and look for the final day of the plenaries and register for that when you can. You'll find it very interesting. My name is Alan DeLuna. I'm the Executive Vice President of the American Astronautical Society. AAS is a nonprofit technical society founded in 1954, and our mission is to advance all space science and exploration activities. We do that through our well-known symposia, such as the Goddard Symposia, the Glenn Symposium, and the Von Braun Symposium. And the Von Braun Symposium is coming up in just a little bit over a month, October 26th through 28th. We also have some amazing technical conferences like our Astrodynamics Specialist Conference, our Spaceflight Mechanics Meeting, and our Guidance, Navigation, and Control Conferences. You can find out about all of our symposia and technical conferences on our website at astronautical.org. That is astronautical.org. We also partner with the folks at ISS National Labs on this conference and lead the effort on these technical sessions. Now, I'd like to thank our sponsors. Our platinum sponsor since the very beginning of these conferences is Boeing. Then we have Jacobs, KBR, Leidos, Oceaneering, Teledyne Brown Engineering, the Engineering and Innovation Technology Development Organization at the University of Alabama at Birmingham. I would like to see the acronym of that one. That'd be interesting. And also be sure to follow us, uh, the ISS National Labs and AAS online. Our various accounts are listed here, and there are a few of them. So we'll leave that up for a couple of seconds. For information about the entire conference, especially the last day of plenary sessions, visit the issconference.org/agenda. That's issconference.org/agenda. Now for today, we have 5 sessions. Here you see them on your screen. I'll give you a moment to read those. I don't need to read them out for you. And we'll take a 15-minute break between the sessions and a 45-minute break at 3:15 UTC. We're using UTC because we have participants around the world, even at this early hour. We have people in Japan and in UAE and in Europe on right now. So we'll take a 45-minute break at 3:15 UTC or 11:15 Eastern. That's New York time. And then we expect to wrap up somehow about 7:30 p.m. UTC or 3:30 p.m. Eastern New York time. Now, moving right into our session. Before that, even before we go into our session, let's talk about Q&A. We have had a really active Q&A presence in this past 2 days, and it's all because our audience goes in and goes into the bottom of their screen and clicks the Q&A button, and then they have a pop-up that says, ask your question. You need to put who you want to answer the question, or you need to put the title or a couple of words of the title of the presentation you're thinking about, put down your question, and then press submit. Now we are only taking questions through the Q&A period or Q&A icon. We are not taking questions through the chat. So don't put your questions in the chat. Put your questions in the Q&A, and we'll be sure to see them. All right. So as I said before, we're working around the world, so we've got a little time education slide for you. I need to use it multiple times a day. So I write it down on my little notepad. All of our times are going to be shown in UTC, Universal Time, or Greenwich Time. And then to get to Eastern Daylight Time, New York Time, you subtract 4. To get to Central Time or Houston Time, you subtract 5. And to get Japanese time, you add 9. So doing a little look at this right now, we see that Japanese time is about 13 hours ahead of us in the New York time zone. And we have people logged in Japan right now. So, our first session, starting now, is Human Health in Space 2. And our session chair here is Angie Bukley. Dr. Bukley is the Assistant Principal Director for Exploration, Science, and Technology, Human Exploration and Spaceflight for the Aerospace Corporation. Now we're going to start with 5-minute summaries for each of the presentations. We'll leave them up for you for a moment to just glance through. Each of our presenters have put in a 5-minute executive summary and a 20-minute full presentation. So if you go to our schedule website, you'll see an opportunity to download those and view them at your leisure. But now we're going to play the 5-minute executive summaries for all 5 of these, front to back, and then we'll be back to you. So play the slides, please.
Hello everyone, my name is Jay Hao, a doctor physical therapy student from the University of Nebraska Medical Center. I'll give this presentation with my advisor, Dr. Su, how treadmill training could be augmented by visual perturbation for astronauts in the ISS. Microgravity-induced muscle atrophy is a critical issue for astronauts in spaceflight. Extended stays in microgravity environments have been proven to decrease the maintenance of muscle strength and alter pattern of muscle activation. The loss of muscle strength could impede their capacity to complete the missions in the ISS. As part of the comprehensive physical training protocol, treadmill exercise have been used in pre-flight phase. The vision system plays a significant role in human sensory motor control and adaptation, given the fact that regular treadmill exercise was not sufficient to overcome the neuromuscular deterioration in the microgravity environment, and the manipulation of visual information could influence the posture and locomotor control. Combining visual perturbation with treadmill working could be a promising countermeasure to maximize the training effects for astronauts. However, knowledge gaps exist in whether and how the muscle activation could be altered by the systematically manipulated visual perturbation, and whether the induced muscle response are gender-specific. We hypothesize that visual perturbation could increase muscle activation during incline treadmill walking, and larger visual perturbation could elicit higher muscle activation. So to answer these 2 questions, 2 experiments were designed. The virtual reality system was utilized as a tool for us to manipulate the visual information and produce the visual perturbation conditions by optic flow. These 2 videos show the experimental settings of this study. In a normal optic flow condition, the optic flow is in the same direction and speed of treadmill walking. The subject will feel like walking through an endless corridor, while in the rotated optic flow condition, the subject would feel like walking through a continuously rotated corridor instead, and the speed of rotation could be adjusted. 28 healthy young adults participated in this study, 18 for experiment 1 and 10 for experiment 2. The walking speeds on treadmill were the pre-specified preferred working speed. For the experiment 1, the visual perturbation was compared with normal condition. There was a combination of 4 treadmill inclination degrees and 2 VR settings, so in total there were 8 sessions. For the experiment 2, the magnitude of visual perturbation was manipulated by adjusting the rotation speed, and the treadmill inclination was fixed at 9 degrees, and each session had a different rotation speed. For each session, there were 2 minutes walking, and between 2 sessions, there were 1 minute rest. The surface electromyography, also known as SEMG, was used to measure muscle activation. The electrodes were attached to the forming muscles during working: the hamstrings, quadriceps, tibias anterior, and gastrocnemius. Root mean square of the EMG was calculated. The EMG was calculated at the stance phase and swing phase of walking. Here are the results and conclusion of this study. For experiment 1, visual perturbation increased the tibias anterior muscle activation at the stance phase during incline treadmill walking. Secondly, the visual perturbation effect was found on the female participants rather than the males. For the experiment 2, higher magnitude of visual perturbation may induce higher tibias anterior muscle activation at the stance phase. Ongoing study with more participants is conducting to confirm these results. Here are the implications of this study to the ISS. Firstly, These results indicate that the potential impact of integrating visual perturbation into regular treadmill exercise to augment the training effects to reduce the muscle deconditioning for astronauts in the ISS. Secondly, the magnitude of visual perturbation should be taken into consideration based on the expected outcome of training. Finally, the gender effects reveal that different muscle response of male and female to visual perturbation, which need to be further explored to identify the optimal training protocol for different genders. This study was supported by the NASA Nebraska Space Grant. That's all of this presentation. Thanks for your attending.
I'm Donna Roberts, and I will be discussing how brain spine excitability is altered in microgravity during parabolic. Transcranial magnetic stimulation is a portable, non-invasive method for measuring cortical excitability by delivering electromagnetic pulses to the brain. When applied over motor cortex, TMS depolarizes neurons in the cortical spinal tract that result in an observable and quantifiable motor response in muscles of the contralateral hand. But TMS can also be applied over various regions of the brain and has been shown to have beneficial therapeutic responses that could potentially be useful for future exploration class missions, such as to Mars. Several of those applications are listed here. And in fact, enhancing cognitive function and performance under stress is the topic of our ongoing Trish-funded study. For all of these protocols, determining the proper dose of TMS is the first step, and it's based on a measure called the resting motor threshold. The resting motor threshold is the minimal amount of electromagnetic power required to move the thumb. Physiologically, the resting motor threshold is a measure of cortical spinal excitability. So, in anticipation of future applications of TMS for maintaining brain health during long-duration spaceflight, the goal of our study was to determine whether the resting motor threshold changes as a function of gravity state. To do this, we collected resting motor thresholds in 10 individuals before, during, and after parabolic flight. To ensure that we could reproducibly target the same location for TMS application along the scalp, even during the dynamic environment of parabolic flight, we created TMS helmets custom cast to each participant's head to minimize any movement. We also performed closed-loop real-time EMG analysis to measure the strength of the muscle twitches induced by TMS in order to determine each participant's resting motor threshold. This is a diagram of our in-flight data collection. All TMS and EMG equipment was strapped to the floor of the airplane just in front of us. 10 participants were divided into 2 teams of 5 each and rotated every 5th parabola during level flight. We administered TMS only during the 0G portion of each parabola, which lasted approximately 20 seconds. And here are our results. We found that motor threshold changes as a function of gravitational state. On Earth, motor thresholds for the group remained stable at baseline, and this was also maintained at our pre-flight measurement, which was performed on the plane while it was parked on the tarmac before the flight. However, during zero gravity, we saw a significant 6-point reduction in motor threshold levels for the group, and this recovered at our post-flight measurement. So overall, subjects required 12.6% less electromagnetization applied to the brain to cause thumb muscle activation during weightlessness compared to Earth's gravity. This suggests that neurophysiological changes occur during the brief periods of zero gravity. The resting motor threshold changes were transient and returned to baseline after flight. And the magnitude of these changes due to the change in gravity state were large compared to pharmacological methods of modulating cortical excitability. So it's difficult to determine the underlying mechanism of our findings. However, several potential factors could have contributed, including altered intracranial pressure during microgravity, which has been previously demonstrated in parabolic flight, possible physical movement of the brain during the alternating gravitational loads, and physical changes in the periphery and the musculoskeletal system. Therefore, further study is needed to further determine the exact underlying mechanisms, but this preliminary study shows that RTMS is a potential important tool for measuring brain activity in zero gravity. And in fact, these results will serve as baseline data, which will facilitate the design of active treatment and pharmacologically based protocols affecting the CMS for future spaceflight applications. As an example, TMS may be useful as an assessment tool for measuring brain activation in microgravity. This is important because the effects of central acting medications, such as sleep medications, and other psychoactive substances, such as recreational beverages, can have quite different effects during spaceflight on orbit than they have here on Earth. As an example, one study reported achieving a 5% sedation rate of a sedative medication on orbit compared with a 60 to 73% sedation rate with the same medication on the ground. TMS may prove useful as an objective measure of altered brain activation in microgravity in response to these substances and medications. So with that, I'd like to thank my collaborators in the Brainstem Laboratory and in the Department of Radiology. I'd like to acknowledge funding support for the study from the Translational Research Institute for Space Health through a NASA cooperative agreement. And I thank you for your attention. I'd be happy to take any questions. My email is listed, so please contact me if you have any specific questions, and also remember to follow me on Twitter. Thank you.
In this paper, we will present the analysis of the biodosimetry data that had been collected from the ISS crew members. The study is a collaborative effort of many investigators, but Dr. L. Fiverson is the one who did most of the statistical analysis that I am going to present. There are a number of evidence in astronauts resulting from exposure to space radiation during missions. One of those evidence is chromosome damage observed in astronauts' blood cells. Since the beginning of the ISS program, we collected blood samples from the astronauts before and after missions. The blood samples collected pre-flight were actually exposed to known doses of gamma rays to determine the radiosensitivity of individual crew members. Post-flight samples were collected at two different time points. The first one was between 2 and 4 weeks after landing, and then the second between 6 months and 1 year after landing. So far, we have analyzed samples collected from 39 crew members before and after missions. In fact, 5 of those 39 crew members flew twice on the ISS. And for those samples, chromosome aberrations were analyzed using a so-called fish technique, in which case we can paint different chromosomes in different colors. And chromosome aberrations that were found in those blood cells were also compared to cytokine levels measured in the same astronauts before, during, and after missions to determine whether there is any correlation between immune status in the astronauts and radiation damage in the astronauts' blood cells. This slide shows the data of total chromosome aberration frequencies in individual astronauts. The pre-flight samples were exposed to known doses of gamma rays, and those data points are represented by the blue circle. The points at the 0 dose are the background chromosome aberration frequencies. The post-flight data are represented by the red triangles. I just want to emphasize a couple of points in the summary slides. One is that our analysis does show that the radiosensitivity determined from the pre-flight samples does impact the post-flight chromosome aberration rate. And the other is the correlation between the radiosensitivity and then the background aberration frequencies. And the age effect that we discovered is also very interesting. And those findings will have an impact on the assessment of radiation risks for the astronauts.
Hello, everyone. I'm Joyce Liao from Stanford University. My talk today is entitled High Resolution in Vivo Imaging and Proteomics Analysis of Eye-Brain Diseases in Space. To summarize a lot of studies, eye-brain changes in prolonged space travel include optic disc and retinal edema, retinal ischemia, choroidal folds. This leads to hyperopic shift and blurry vision at near. There are also dramatic shifts in the brain, midline structures, and brainstem. These changes, some are reversible and some are permanent, and there are no current countermeasures. We propose that in order to better understand eye-brain diseases in space, we need to perform more imaging in space. In particular, the imaging should be expanded so that consistent multimodal imaging is performed. This includes the optical coherence tomography B scans and volume scans that are currently being done as part of the ocular health study prospectively. In addition, we could consider algorithms that look at deformation of the eye as a result of eye movement by looking at eccentric gazes 30 degrees in the abducted and the adducted positions. This will help us better understand the changes in the optic nerve head when the astronauts are looking straight versus when they're looking in eccentric positions. In addition, near-infrared reflectance imaging, which is performed consistently as part of the OCT imaging, can be further analyzed to look for subtle evidence of choroidal folds. This does not require any extra analysis, but merely some training. Finally, OCT angiography should be performed in space so that we could understand and characterize the vascular compromise in the setting of retinal edema and ischemia. To better understand why some astronauts develop eye-brain diseases, it's important to not only perform prospective ophthalmic imaging, but also to obtain blood to analyze the DNA as well as plasma proteomics in order to understand who is more likely to develop SANES and how to mitigate it. At the same time, we could also track the physiologic parameters such as heart rate, blood pressure, oxygen saturation, etc., in order to understand all the factors that correlate with the development of SANES.
So what is AstroRad? Well, AstroRad is personal protection for astronauts venturing into deep space, where they would be potentially exposed to solar particle events, so very different from the environment in ISS or previously on the space shuttle, where astronauts were protected pretty well by Earth's magnetosphere, which is quite efficient, or very efficient actually, at repelling solar particles. So in the absence of this magnetic shield, we're basically looking at making personal protection through a wearable solution called AstroRad, a solution that focuses protection on the body's most vulnerable organs. The product is currently on station undergoing ergonomic studies through a collaboration between the Israel Space Agency and Lockheed Martin. And next year, it's flying around the moon on Artemis 1 to validate its radiation protection benefits. And that's a collaboration between NASA, the Israel Space Agency, and DLR. So in making any kind of radiation protection solution, you have to recognize that, the number one principle enshrined in the art of radiation protection is A.L.A.R.A, which is short for as low as reasonably achievable. And what is meant here? What is meant really is that if you want to protect, make sure A, that you're providing meaningful protection, and B, that meaningful protection is not disturbing or impeding the function of that person, be it a firefighter, a police officer, or an astronaut. So our testing strategy for AstroRad is coming to validate that indeed what we're doing here is abiding with A.L.A.R.A. So first of all, validating that it's protective enough, that it's reducing the dose to an amount that is low enough. We're going to test the solution within the MILSTEIN experiment, MILSTEIN being short for Matryoshka AstroRad radiation experiment, which is our collaboration on Artemis 1, on Orion, to go around the moon and collect very valuable data as far as the protective benefit in deep space. I'll mention MILSTEIN a bit more as we go forward. And then the other pillar within our testing strategy is charge, and that is on ISS, and the goal there is to confirm that the product is comfortable enough, ergonomic enough, useful for the astronauts, not only protective but also streamlined with their needs as astronauts. The combination of these two data sets will enable us to A, confirm that we have something good going for us here, but also to improve down the road. So currently on station, we have a vest. This is a project, basically a payload that was delivered through a collaboration between Lockheed Martin and their Israeli Space Agency. We as StemRad served as a contractor to the Israeli Space Agency. We're very thankful on this collaboration, both to Lockheed Martin and to the Israeli Space Agency for their support. The plan here is for 4 crew members to wear the vest. The vest was made for females based on their organs, but it can be worn by males of a smaller build. So we're basically briefing astronauts across the board. We currently have 2 astronauts that are slated to fly at the end of this year or early next year that are going to be wearing the product. Testing will be taking place until the end of next year. The goals is basically to find the level of ergonomics, if they're compatible with their needs through checking range of motion, comfort, and the general user experience. We're going to demonstrate also the adjustability capabilities of AstroRad, meaning that we're making a product that could fit across a limited number of anatomies, but still can fit across through adjustability mechanisms. So will that work as good as anticipated? And we're really looking forward to getting the crew feedback that will drive optimization and design improvements of AstroRad. And that's ongoing on station. And yeah, there she blows, and the cupola on ISS, a picture taken by astronaut Jessica Mayer a few months ago on station, and very happy about having it there. We're looking forward to crew wearing it and to receiving their feedback.
All right, so I'd remind you now to go in and do questions for the presenters. Go to the bottom, click Q&A. We've got 2 already. We should end up with a lot on these presentations. So click Q&A, type in your question, and hit submit. Now, Angie, please come in and introduce your panel. Then I'll come back to you. Angie, you need to unmute your button. There you go.
Okay, sound check. Yeah, great. It's my pleasure today to introduce our panel. We will have Ji Hao from the University of Nebraska Medical Center. We'll have Donna Roberts from the Medical University of South Carolina. We'll have Honglu Wu from Kennedy Space Center, who briefed the chromosome damage and had a very large team of authors on that paper. We'll hear from Joyce Liao from the Byers Eye Institute at Stanford, and finally OREN MILSTEIN from StemRad. And that is our panel for today.
All right, and I'd like to introduce Ayaka Ito. Ms. Ito has a question for the panelists. Ms. Ito, can you activate your screen and audio and ask your question? I'm sorry, Mr. Ito. We're trying to get Ayaka onto the screen. Just a moment, we'll dance for a minute, waiting for them to come in, except I don't dance very well, so I'll do card tricks. Waiting. Bueller. Okay, we're going to give one more chance here. Okay, we will go ahead and start with your questions, Angie, and if we're able to get Ayaka back in, we will come in and interrupt you. So go ahead and move forward, and thank you for taking this panel, and thank you for panelists for being tolerant of our delays here. All right, let's go.
All right, well, thank you for that, Alan. And first of all, I'd like to sincerely thank the panelists for taking the time to put together your presentations ahead of time. This is my first virtual experience in a conference, and I don't know if it's your all's first experience, but hopefully it will continue to go smoothly. We do have one question that's been submitted in the Q&A session, and that's from Raghavendra P. And this is, I assume this is a question for Donna. And the question is, are the long-term influences of microgravity transient as well?
Yeah, thanks for having me. Really appreciate it. Enjoy the session. And thanks for the question. So are the long-term influences of microgravity transient as well? That's a very general question, and it really depends on what specific factors you're discussing. Our work was particularly aimed at understanding physiological changes of the brain during spaceflight, and there's very little research that's been done in that area to date. In addition to the microgravity parabolic flight work that I presented today, we've also done some brain imaging studies of astronauts before and after spaceflight, and we found significant changes in brain structure that's occurred after spaceflight. And at follow-up imaging, months to years later, those changes, there are still residual changes. So I don't really think that some of these changes are as transient as we might think that they are, but more research needs to be done in that area. Thanks.
Well, thank you very much, Dr. Roberts. We have another question that's come in from Paula Janik, and it's for Dr. Howe and Dr. Su from the University of Nebraska. And the question is, were BMI, body mass index, or other physical variables, that is not just gender, made?
Okay, thanks for your question. For this study, we mainly include the subjects of the unhealthy young adults so that their BMI and other physical variables, I think they are very normal. So I didn't. So in this study, we didn't look at this index.
Okay, thank you. Well, there was another question, but it disappeared. The only one I see is the one I just asked. Let me see if it popped over to the other place. Yeah. Oh, okay. This one is for OREN MILSTEIN at AstroRad. It says, since GCRs are unshieldable, is the vest going to be used by astronauts during solar SPEs, solar particle emissions, I guess?
Yeah, thank you, Angie, for hosting us here. And yeah, it's a very good question. So GCRs are very difficult to shield. So the primary use case here is for solar particle events. So that's correct. At the same time, we are always trying to improve and look for solutions for GCR. And we did find that there is an attenuation of approximately 10 to 15% of GCRs as far as reduction of effective dose using the vest, but they're ongoing all the time. So it would require long duration use of the vest, and it's not practical for them to wear it all the time. But when they're sleeping, we think that it could be something that is not intrusive and does not really inhibit any of their functions. So I would recommend wearing it during sleep if it's comfortable enough to just enjoy the reduction in 10 to 15% of GCR.
Okay, well, thanks for that.
And
to
Angie,
follow,
this is Alan.
yes.
We've put Miss Ito's or Ayaka Ito's question into the Q&A tool for you. And again, reminding the panelists, please do not type answers into the Q&A tool because it causes the question to disappear and Angie can't see it to ask the question. So please do not type the answers in. I'll wait for Angie to come and give it to you. Go ahead, Angie. All
right, thank you. And you can remove the question from Paula because we've already addressed that question. Thank you. Here's another question that is directed toward you, OREN MILSTEIN, and it has to do with, is there a specific thyroid protection as well that would be part of the vest?
Right, so thank you. So thyroid is really an organ that you want to protect. It's fairly sensitive, not as sensitive as the bone marrow or other internal organs, but it is, and it got a very big stage during Chernobyl, where young children, they were drinking milk from cows that had been foraging on fallout from the reactors. And that material got incorporated, the iodine 131, got incorporated in their thyroids and caused awful thyroid cancers. It's something very well known. I'd like to point out that most of the sensitivity of thyroid is due to exposure to iodine 131 through inhalation and ingestion, not necessarily through external exposure. Here we're dealing, thankfully, only with external exposure. It is good to protect we have partial protection of the thyroid, but to protect it completely, just the ergonomic effect would be too challenging. So.
Okay, thank you for that. Let's switch over to Dr. Wu, and this question again is from Paula Zenick, and the question is, which type of chromosomal aberrations were measured?
Yes, so let me get into the details of the methodology there. I think that's what this question is about. So we draw blood and collect white blood cells, and then we harvest chromosomes. So the methodology we use is to what we call fish. So we paint different chromosomes in different colors. And in principle, we analyze all different types of chromosome damages, and mainly translocations, deletions. We also classify those aberrations as a complex type. Complex because the space radiation is mainly high LET, heavy ions, so they produce different type of chromosome damage than X-rays or gamma rays. So we analyze and we score all different types of damages. But the data I presented is only the total damage. Since the crew members are exposed to chronic radiation, and typically the damage that survive a 6-month mission will be what we call stable, or translocations mainly.
Okay, thank you for your answer. I'm going to exercise my authority here as the session chair, and I want to ask a question of Dr. Joyce Liao. Joyce, I want to know, I know quite a few astronauts living here in Houston, and I have the opportunity to meet and talk with them from time to time. And most of the astronauts I know personally, after flight and beyond, experienced loss of vision. Not necessarily, not everybody gets SANS, we know that, but they experienced, some loss of vision. So I know that SANS is an issue that, everyone is struggling with. Have you made any correlation, any kind of correlation to show what indicators? I know you showed a lot on your last chart, but which is the strongest candidate to tell you who might be more susceptible to SANS?
Thank you so much for the question. The measurements are typically done post-flight. So, a comparison of pre and post-flight using high-resolution eye imaging, on Earth. And these are typically done in micron resolution, so 10 to the minus 6 meters. In comparison, the brain imaging is typically more in the order of millimeter. So it's a couple of order of magnitude different in terms of better resolution. The most important indicator of blurry vision. It's typically not vision loss, but more of an alteration in vision is whether there is a presence of optic disc edema or not. So meaning inflammation and fluid accumulation in the back of the eye. If you have fluid accumulation there, it has a strong distorting force locally. So that when you are trying to see, which is, photoreceptor neurons in the back of the eye, that optical distance and the sensitivity is altered. So essentially the presence of inflammation or edema is likely the most important indicator. There are others such as microhemorrhages, or what we call cotton wool spots. These are basically evidence of ischemia that really kind of accompany the presence of edema. But essentially, the most important issue is the presence of edema, and then the wrinkling of the eye, which gives you the folds, and et cetera. These are basically residual evidence of that. I think for MRI, there's this sort of upward lift of the brain structures. In the eye, it's all about wrinkles.
Okay, thanks for that. I got one more follow-up question for that. Have you noticed any correlation in the susceptibility to age? Because I know in your presentation, you showed a picture from a 57-year-old astronaut. Have you made a correlation with, say, some of the younger people who have been flying?
Age does not seem to be the strongest indicator. There are probably structural and potentially genetic mechanisms that are indicators. I have not seen this published, but I've been told that it's possible that women may be less susceptible to SANS. I have not personally seen the data, so I can't speak to that. But there were suggestions that perhaps for the flight to Mars that we should be thinking about female astronauts.
Oh, I concur fully. Yeah, I had read the same. So thanks for your answer. I've got a couple of questions for you, Dr. Roberts. and with regard to your microgravity flights and the research you did there. Have you considered doing variable gravity flights? Like we've done several variable gravity flights over with in Europe on their platform, flying at well, we've done lunar gravity, Mars gravity, 1G, 0G. We've also done 0.25, 0.5, and 0.75G. Have you thought about what your data might look like if you look at it in a variable gravity regime?
Yeah, I think that's a good question, and yes, we have thought about doing that, and I think that's probably a next potential step. Our study was really just a pilot study to prove that we could do it, and to see if there was going to be a difference or not, and so I think that would be a great follow-on step.
Okay, and did for your 1G situations, I noticed you did some ground studies. Did you also take measurements during the straight and level 1G portion of the flights?
We didn't do that, and we also didn't take measurements during the hyper G part of the flight. There was so little time in between to be able to accomplish all that. And during the straight and level part of the flight, we were concentrating on changing positions between the operator and the subject. So we didn't really have a lot of time to do all that.
Right, those things happen really fast.
Exactly,
I've
yes.
been there, done that. So two more questions, and I'll go ahead and just give them both to you right now. Were the subjects on any medication to prevent, getting sick? And the other one, were they seated the entire time? Did you do any free floating analysis?
Yeah, so yeah, that was a good question. We really struggled with that before our flight because we didn't want to risk changing the data based on everyone taking medication, and most of our subjects were first-time flyers, so it was really a concern. We spent a lot of time practicing the movements in order to avoid head movements that would have been provocative. We got some help from Dr. Mark Shellhammer, who has had a lot of experience flying these flights, and he kind of coached our team through some of this. So we ended up not using any medications for the flight, and everyone did pretty well. We all were seated before our turn as subject, and only afterwards did subjects were allowed to free float. So I think that really helped prevent any episodes. And so there were a couple of us who got sick afterwards, but that was after their measurements had already been taken. So we were pretty lucky in that regard.
You got really lucky. So great. Well, congratulations. I have another question that's come in on the Q&A, and it looks like this one might be directed more toward Dr. Liao. And the question is, does flying constantly on a parabolic, I think they mean in parabolic flight, 0Gs, also have the same effects on the eyes? Have you done any experiments in parabolic flight?
I have not personally, but this has been published by Dr. Byron Lam at University of Miami.
Okay.
They had a patient who underwent brain surgery. So there's actually what's called a bolt, to measure the brain pressure. And they took this subject on a parabolic flight. The idea is to test whether there is evidence of increased intracranial pressure, thus causing the optic nerve swelling. And what they found was actually the opposite. So they found, at least in that experiment, that during parabolic flight, the brain pressure actually decreased, at least, transiently. And so they argue that at least, in that kind of increased G situation, that it does not induce intracranial pressure. So this is why we still don't quite know why the neuroocular syndrome occurs in space, because it's truly extraterrestrial.
Okay, thank you for your answer. I've got a couple of questions also for Dr. Wu. And in your presentation, you talked about a method called FISH. Could you tell us what FISH stands for and a little bit about how that method works? And also, does it turn out that the older the subject is, the worse the effects are?
Yes, and if you let me start with the FISH. FISH stands for fluorescence in situ hybridization. So basically, I mean, with a human, you have 23 pairs of chromosomes, and to analyze the damages, you have to I use the word quote unquote paint the chromosomes. There are some old technologies where you can analyze dicentrics and where you can identify the centromere of a chromosome. But then that's not efficient for stable type and operations that we observe in the astronauts. So we use this FISH, and we paint 3 different chromosomes. And usually we want to paint the large chromosomes, so to have a larger target size, and in 3 different colors. And then when a chromosome, for instance, chromosome 1 is broken and has a translocation event with another chromosome, then this method will be able to detect. So that's considered a gold standard for biodosimetry and for many, many years now. Although these days, I mean, there are different type of methodologies out there to use as a biodosimetry, like a gene expression, things like that. But then still, chromosome damage is still considered a gold standard. I'm sorry, I forgot your second question.
Oh, correlation between age.
Oh, yes. Yes, actually, that's an exciting finding from this particular study. So let me just start with the background. Okay, the background, okay, in the audience. And typically, I mean, we found is that the older people older crew members will have a higher background level. And that's kind of expected. And this is known previously too, because I mean, older people will experience more environmental toxins, I mean, through your life. So, and that's expected. But then what we found was that then the older crew members will also have a higher radio sensitivity. And they seem to respond to radiation more than younger crew members. And that's kind of interesting because we always think that the older astronauts will have less radiation risk. That may or may not be true.
Interesting. Well, thank you for your answer. We've got a question in the Q&A box, but I'm going to ask a couple to Dr. Howe, and then we'll come back to OREN MILSTEIN, Dr. MILSTEIN. So, Dr. Howe, how do you explain the difference in performance between men and women in your experiment? You saw that the women responded more to the visual stimulus than the men do. Have you figured out why that might be?
Yeah, okay. Yeah, that's a very good question. So we think that the difference between muscle activation of male and female maybe the visual perception issue. Yeah, because when they're actually the male and the female, they see the same VR condition, but they have different response. Yeah, so this means that in their central nervous system, they may interpret this visual perturbation differently. Yeah, so maybe female is more susceptible to the perturbation. Yeah, so there is a difference between male and female in the visual processing and the visual perception. So this may be the issue. Yeah.
Angie, maybe you're on mute.
Yeah,
Angie, you're muted.
Yep, it flashed. When you had your subjects on the treadmill and you had the rotating scene, did you have any issues with them losing their balance or feeling a little off kilter?
No, based on our observation during the study, maybe they are healthy young adults. All of them performs very well. Yeah, they didn't have loss of balance or deviation issues.
Okay, thank you for that. So let's jump back to Dr. MILSTEIN, and we have a question from Ito, and it says, when or in what situation do astronauts wear the AstroRad? For example, do they wear it during the IVA, EVA, or something like that?
Right. For today, the use case is within the spacecraft. So that would be an IVA, just to wear it over your normal clothing during a solar particle event, or as I mentioned before, if you choose to avoid GCRs as much as you can wear it for as long as you can endure, especially during sleep. In the future, we are looking at develop an EVA version of AstroRad that would be integrated into the EVA suit, but that is still a bit far off, but we're hopeful that in the future that will occur.
Great. And another question popped in for you from Rajarshi Chowdhury, and he wants to know, what is the mass penalty for each AstroRad vest, and is there any way to reduce that mass penalty or the mass of the vest in the future? And will they be useful for surface stays, for example, on the moon or on Mars?
Very good question. So we've done everything possible to reduce the mass penalty through our selective shielding technology. So we're focusing protection on the most sensitive organs to get the best punch per kilogram possible. We're also accounting for the body's self-shielding around each organ to create a variable thickness that is thicker where you have less self-shielding, so on and so forth, and thinner where you don't. That said, we're proud today to let the world know that we are working with Made in Space, which is a company that is able to print things in space. And the purpose of that collaboration is to utilize onboard waste materials, such as packaging material, that tends to be rich in hydrogen-rich polymers that we could use as radiation shielding material. So the idea would be to reprocess, so to grind down that waste and basically use that as feed material into an onboard printer, possibly in a lunar gateway situation, or maybe on the moon or in Mars, where you'd be able to use parasitic mass towards creation of some of AstroRad. That's long into the future, I would think, but any kind of reduction in the penalty is welcome. Even a 10 to 20% reduction would be great.
Awesome. Thanks for your answer. So we're coming up close to the end of the session, and I've got a good question here from Jeff Bingham that's directed to any panelist or all of the panelists, and it's a very general question. It says, do any of your findings potentially serve to remove or address apprehension on the part of lay citizens to participate in low Earth orbit spaceflight? Have any of your discoveries might make somebody, more interested in flying in space? Anybody?
Well, at least for eye conditions, I could say that it doesn't seem to occur for a very short-term flight. So that should not be a limitation for doing the short-term space exploration.
Thank you. OREN, would you care to comment? Because you're working on something, but that's really not so applicable to low Earth orbit. But
yeah,
anyway.
I think yeah. I mean, it's clear to me that you can be within lower Earth orbit without incurring too much radiation damage. We've had astronauts that have been there for a year, and while they have received doses higher than normal by far, still their health remains in good condition. So I would not be concerned about the radiation effects for a short duration flight in LEO.
Yeah, I have to plug a study we just finished that indicates in terms of dose rate, you get the same dose rate doing a high altitude, long duration flight over the pole
Right.
as you do on the ISS. So the dose rates are comparable. So I thought that was interesting.
Yeah.
So that's it. We've come to the end of the hour. So respecting the time, I'm going to pass things back over to Alan. And thank you all for your participation today. I think it went really well, and I really appreciate your answers. Well done.
Thank you, Angie.
Thank you very
Thank
much.
you, Angie.
Thank
you,
you,
panel.
everybody.
Alan.
Thank you.
Thank you, Alan.
And relating to your last comment, Angie, until about 4 months ago, we'd get the same amount of radiation flying over the poles. Now nobody's flying over the poles, and we're staying home.
That's true.
All right, so thank you all. This has been really interesting. The audience warmed up and started really throwing in questions after a little while, and that's great. So you encouraged them and you enlightened them, and we think we had a great panel. Now we're going to take a little break until 2:15 Universal Time or 10:15 New York time. We'll reconvene in the same place for novel concepts and advances for space operations. Jim Wade will be coming on and seeing y'all in just a little bit.